Hello everyone. In this video we are going to talk about a topic in computer vision called structure from motion, or SFM. And this is an important and very interesting topic. Before I start, I need to mention that the pictures, equations, and the code are taken from the book Computer Vision Algorithms and Applications by R. Zaleski, and also from MathWorks. So I don't claim any ownership on anything here. I'm just explaining the material to you. So what is a structure from motion? This is the problem of you have a camera, you take several pictures from the same object from different angles and from different locations, and then using these pictures you want to what? You want to reconstruct the 3D model of the environment, right? So here, like I have the small cup in person's hand, and I take different pictures, as I said, from different orientations and locations, and I can make the 3D model of that scene, as well as finding out from what angles and from what positions those cameras were taken. So I want to estimate the pose of the camera as well as the 3D geometry, which we call a structure and motion. And you do it at the same time, simultaneously. You have not recorded where and at what position and what translation and what rotations you have taken those images. You don't know, and you don't know anything about the 3D geometry, okay? And you do that just by a few set of corresponding feature points on the images. So for instance, you say, hey, this blue point here is the same as that blue point, that red point is the same as red point, this green point is the same as green point between these two pictures, or you might have several pictures, and from those correspondences you want to estimate both of these information. And you have probably might use some apps on your phone that you go around with your phone around some object and take several pictures, and then it creates the 3D model for them. That is this guy here. So those apps that you use on your cell phones to take pictures and create 3D models, those are using a structure from motion. So how does it work? What is the mathematics and what is the explanations behind the scene? This is what we're going to see. So as I said, it has applications from 3D scanning, which I said you can do with your phones, from augmented reality, and also in Visual SLAM, or VSLAM, which is Visual Simultaneous Localization and Mapping. So it has applications in robotics too. Okay, so what do we do here? The one that we're going to look here right now is the SFM from two pictures. And then I explain that if you have more than two pictures, what is it that's going to happen? So right now, let's say you have two pictures. So this is kind of like stereo. And here you have this 3D point P, and you have two cameras, one on the left, one on the right, and you take pictures of this point P. The centers of these cameras are point C0 and C1. And the projections of this point P onto the camera plane, or the pixel coordinates of P in those two frames, are x0 and x1. Clearly they are not at the same exact pixel because they have different rotations and different positions, right? So x0 and x1 pixel coordinates are not the same. The distance along this line C0 P, or along the line X0 P, okay, this distance we call it D0, and the distance from X1 to P we call it D1, okay, right? So here we have some new terminologies that I want you to know about. First of all, the plane formed by the center C0 and C1 as well as your 3D point is called the epipolar plane. Okay, this triangular plane is called the epipolar plane. What else? Now, if you move this point P along this line PX0, if you move it along this line, and project all of these different points onto the right image, you see that all of these projecting rays should pass definitely through point C1. These points will all form all of these new projection points, and if you basically connect all of these projections to X1 and continue, they form this brown line on the right image, which we call the epipolar line on the right image, and also what? The epipolar line on the left image. So this one on the left image is also what? The epipolar line, but this one is when you basically move the point P onto the line P1x1. So if you move it on this line now and connect them all to C0, then you can see that all of these projection points along with x0 will form this line on the left image, which we also call epipolar line on the left image. So we have two epipolar lines here shown by these brown lines. We have the epipolar plane, and then we also have these two locations, E0 and E1, which we call them what? The epipoles, which are the intersection points of what? Intersection points of these epipolar lines with what? With the line that connects the two centers, C0, C1. If you intersect this C0, C1 with this epipole line, you get E1. If you do it with the other epipole line, you get what? E0. So these are some terminologies that I want you to know before we jump into the mathematical description. So what is it that we have here? What is it that we need to find? The things that we have here are point x0 and x1. We do have these points, and we know they correspond to the same 3D point, P, that we need to find its xyz. And we also need to know the position and or the translation and the rotation of one camera with respect to the other one. In other words, if we say that the location of the left camera is 0, so we set the left camera at origin of the word frame, and we say that the rotation for this basically coordinate frame that is attached to camera on the left, right? So it's something like this, let's say. If we say that the rotation matrix for this frame is R0 equal R equal I, identity matrix, then we need to find what? We need to find the location of this point C1. So if we show it by this translation vector t, we need to find the vector t, the location of the second center with respect to the first one. And if I attach a frame here to the second camera on the right, and it is something like this, and this guy has a rotation matrix R, I want to know what is that rotation matrix. Okay, so x0 and x1 are given, their pixel values, and we assume without loss of generality that these two are 0 and identity. We want to find t, we want to find r, right? So these two together are called the pose of this right camera, and also what? The location of this point P in the word frame. This is mathematically what we're going to do. So how do we do it here? Well, so let me move this to the next line so we can write a little bit nicer. So we can say that if we project the point xj, which could be x0 or x1, these points, if we project them onto the camera frame and call it the same xj but with a hat, so xj hat, what's the difference between xj hat and xj here? the point xj is the projection onto the camera frame, so it is something like u and v, right? But xj hat is what? It's the coordinate of the point P projected onto the camera frame, okay? So you projected point P, which is in the word frame, you brought it into the camera frame, so it is something like x, basically I and j and y, I and j and 1, right? A homogeneous coordinate. You know these two are related to each other by what? And we also have this point P in the word frame. You know you go from the word frame to the camera frame through what? Through that R and T. And then you go from this camera frame to the pixel coordinates through the camera intrinsic matrix K, right? So xj hat is what? K inverse times what? Times xj, because here you clearly see that this xj is equal to k times xj hat. So if you want xj hat, you have to multiply both sides by inverse of k, or kj, where j is the jth camera. So if it's 0.1 or 0.0, that's camera 0, which is the left one. If it's 1, then it's the right camera, right, for j of 1. So this hat again is the point in the camera frame, not the pixel coordinates. So I can write x0 hat, right, here as connecting this origin to this projection point, right, in this direction. And if you basically multiply this distance d naught by that direction, it will get you to what? It will get you to the word frame point P, right? So this distance d naught in this direction, right, from this location will give you that distance, knowing that this distance is very small, correct? It's just the focal length, which is much smaller typically compared to this distance. And then this direction, which you might call it x1 hat, so this was x0 hat. If you multiply it by d1 again, that will also lead you to point P. So here we are going to rename or denote basically that d naught x hat, right, the projection of P onto the left camera frame, as P naught, and d1 times x1 hat, which is the projection of P onto the right camera frame, as p1. We know we can relate this p0 and p1 together using a rigid body transformation. So p1 can be written as r p naught plus t, where r and t are those two parameters for pose of the right camera. And so if you plug it in, then you'll get that d1 x1 hat equals r p naught plus t, and for p naught you replace d naught x hat, so you get this, right? So now what you have is basically this one equals this, right? You get d1 x hat 1 hat equals r d naught x hat plus t. Now, one thing before I move forward that we assumed is we can calculate this x0 hat and x1 hat by what? By multiplying the k inverse, the intrinsic matrix of the cameras, by the pixel coordinates. Because what we really have is just x, we have the pixel coordinates, but if we also have the camera intrinsic matrix, we can have the projections of the P onto the camera frame, that x, y, and 1. We can get these, and we can relate them together by a simple what? By a simple rigid body transformation. So here we assume that we know the K matrix. right? That is a very important assumption. So the camera should be calibrated. We have the camera, we know the information for the camera, and now we have this equality. Then what do we do here? The first thing we want to do is to get rid of t. How do we get rid of t? We cross multiply both sides by vector t. So we bring t from both sides and we cross multiply. So this guy becomes, this d1 is a constant. It comes out, so it becomes d1 t cross x1 hat. And the right hand side becomes, again, d0 is a constant, comes out. This r can be multiplied by x0 hat to give you a new point. And then t cross that, so it's going to be this one. And then t cross t, this is going to be 0, right? So this is like plus 0. Now, another way you can write it is, as you know from skew-symmetric matrices, if I have a vector t and if I write it as the skew-symmetric matrix of vector t, which here in this notation is shown instead of st, it is shown by tx, right? That's the same notation. Then I can say that t cross any vector a can also be written as this skew-symmetric matrix of t times a. And here I can write cross product as a matrix multiplication. And this one, if you don't remember it, this is a skew-symmetric matrix where on the diagonal you have zeros, and then here basically you have, if this t vector is like t1 and t2 and t3, or tx, ty, tz, this is going to be basically t3, t2, and t1, where 1 and 3 are negative and 2 is positive, and the mirror image of them are going to be negative of them, since it's a skew symmetric or anti-symmetric, you might go. So it's something like that. Okay, so you can also write it in skew symmetric form notation. You replace this cross product and you can write it like that. It's all matrix product. So far we got rid of t. Now we want one side to be equal to 0. So what we do, now we apply a dot product on both sides with vector x1 hat. So now we do what? x1 hat dot both sides, and as you know, instead of writing vector a times vector b in linear algebra, we can write it as a transpose times b. Right? We can do it also as, again, a matrix product. Right? So here, that's what we do. We use a x1 transpose as a dot product, and we multiply by both sides. Again, d0 and d0 can be taken out. They are constant. And now here you'll get what? You'll get x1 transpose t rx hat. Remember here that in this equation I swapped the two sides. And on this side you have t1 x1 transpose tx1. Now what is this guy here? This guy is like x1 hat dot t cross x1, right? So this one here, if I write it, this is x1 hat dot x1 or t cross x1 hat. And what is this? As you know, this is what we call a triple product, and it shows the volume of the parallelepiped formed by these vectors. And since two vectors here are the same, you can show that this guy is always 0. So when 2 out of these 3 vectors are the same, this is always equal to 0, this volume. Because you can never form a volume here. You just get a parallelogram, and volume of parallelogram is 0. So now this is 0. And this d0 is a constant, so you can simplify from both sides. So now what you get is this guy here. That this one in this first box is equal to 0. Now, if I call this T skew symmetric times R, if I call it matrix E, which we call it the essential matrix, then you can write this top equation as x1 hat transpose E x0 hat equals 0, and this is what we call the epipolar constraint. So you can show that between any two corresponding points from the left image and the right image, x0 hat and x1 hat, there is always this relation. They are perpendicular to each other with respect to E. This is another way we describe it mathematically. We say x0 hat and x1 hat are perpendicular to each other with respect to matrix E. We call it epipolar constraint, and this E, again, you see it involves both of the vectors and the matrix that we needed for the pose. So this E has both translation vector and the rotation matrix. And this is the goal, is to estimate this T from a bunch of x1 hat and x0 hat. And once we have E, hopefully from that we can estimate both T and R. And again, this E is called the essential matrix. So now how do we go about estimating E? The first thing you need to know is that, remember here that x1 E x0, x1 hat, E x0 hat is 0. This can also be written as, if I call this second portion of this L1, I can write it as x1 hat L1 equals 0, where L1 is EX0 hat, okay? And what is that? Remember, x1 hat is this direction. If I go back and do a little bit of cleaning, because this is too messy here, x1 hat is this direction. This is x1 hat. If x1 hat, right, transpose times some L1 equals 0, then this L1 should be a direction that is perpendicular to x1 hat, right? Because you know, when A dot B is 0, that means these two are what? They are perpendicular to each other. So which direction here I have that is perpendicular to this? That is this line here. Now here seems like I have a notation problem. This is L1, sorry. And this is L0, not L1 and L2. Yeah, you always get some typos. So this L1. So L1 here is what? This epipolar line. Okay. What does that mean? Remember, L1 was what? L1 was E times x0 hat. So what does it mean? It means that this point x0 using the E matrix is mapped into what? Is mapped into line L1, and that is obvious from here. Okay, and similarly you can show that x1 using E can be mapped into what? To line L0. Okay, yeah, so mathematically just keep that in mind. Now, from your linear algebra knowledge, you can show that since lines L1 and L0 pass through what? They pass through these epipoles, point E0 and E1, right? And with these properties that I mentioned, you can show that then these points E0 and E1, or the vectors associated with them, are the zero value right and left singular values of E. What does that mean? Means if you write E in singular value decomposition, right? So you write it as U times a sigma times V transpose, right? And this U has three vectors in it, which we call left singular vectors. And this V are the right singular vectors, and this sigma is the matrix of singular values. Then this is something like this. So you get U0 and then U1, right? And here is a 3 by 3 matrix, and here you get a bunch of transpose like this, So as I said, this is like U0, U1. Here is going to be E1. Here you're going to get sigma 1 and sigma 2 and a 0 here, because this E matrix, you can show this matrix is a singular matrix. It had one singular value or eigenvalue of 0, and then everywhere else is of course 0, right? And then here you have basically, so here you have V0 transpose and V1 transpose and E0 transpose. So you see that E1 and E0 are the left and the right singular vectors corresponding to the singular value of 0. That's why we call them zero value, means singular value of 0, right and left singular values of E. So you can find the epipoles, of course. If you do SVD, singular value decomposition, on E, you can definitely find the epipoles, okay? But is that enough? No, we need more than that. So first thing first is, how do I find the entire entries of this matrix E, right? So first you have to find matrix E, then you apply any singular value decomposition or anything on it. How do I find E, right? Because I don't have E. All I have is this x0 hats and x1 hats, which I found by what? By basically finding points x0 and x1 and then applying k inverse on both of them. Okay, so that's all I have. I only have this. This E is unknown. First of all, how do I do it? Well, I go back to this equation and I try to use this equation and expand this equation. So I expand this equation. How? This is what we do. So we need at least 8 corresponding pairs of points on the two images. Remember here, this green point corresponds to green point, blue to blue, red to red. I need at least 8 of these correspondences. Okay, so here that's 1, this is 2, this is 3. I need 5 more of them at minimum to be able to find E. And you might say, why 8? I'll tell you. What is the dimension of matrix E here? Remember, these x hats are of form what? These x hats of a form basically this, right? They have some x and some y. So here I need to add a hat here. So they have 3 entries. So when this is equal to 0, that means dimension of this E is 3 by 3. So it has 9 entries. So if we need 9 unknowns in E, we need to have 9 equations. But remember that this E has a determinant of 0, so we really need 8 of them. And so we need bare minimum of 8 corresponding points, xi0 and xi1 hat, both of them, where I goes from 1 to 8. And if we do that and expand this equation in terms of the entries of E, so here I write my E as what? I write it as E00, and then E01 and E02, and then here E10 and E20 all the way to E22, right? So if I want to write all of them here, so it has 9 entries, but again, since its determinant is 0, that's an extra constraint, so we only really need 8 equations. And so if you expand any of these equations for any I, so this x1 is first point and x0i, if you do it, they all look like these. All of these 8 equations from these 8 pairs, they all look like this equation number 2. Where all of this here on the left-hand side, which is that product, should be equal to what? 0. So you have one equation here, right, with 8 unknowns. All of these e's are unknowns, right? And all of these x's and y's are known. And how many of these you have here? I goes from 1 to 8. So you'll get 8 equations and 9 unknowns, but remember these 9 unknowns are not all independent from each other, so you should be able to find them all up to a scale. And that is the next thing we have. We cannot find all of the 9 entries of E uniquely. We can find them all to a scale. What does that mean? Means, for instance, we set one of these E's equal to 1 and then find the rest of them, right? Like that's what we call normalization when we did eigenvalues. That's the same thing. We find one of them, we scale one of them to 1 or whatever fixed number, and then find the rest of them, okay? And clearly you see it's 8 linear equations and 8 unknowns, so it's not really that hard to do it. Another way to write this equation too is, if you want to write this in a matrix format, you can also write it as this here, that xi1, right, times xi0 transpose, and then dot multiplied by E equals 0. What does that mean? Remember, your xi here is a vector, right? This guy is a vector and this guy is a vector. So here you have the first one times transpose of the second one. So this goes like this. If we go with the same notation as we had above, this is xi, right? And here j is 1. So it's going to be xi and 1, and then yi and 1 and 1, correct? Times transpose of the other one, which is like this, and that is going to be xi0, yi0, and 1. And when you multiply here a 3 by 1 by a 1 by 3, you'll get a 3 by 3. So this guy is going to be a 3 by 3 matrix. And remember, E is also a 3 by 3. So both have the same dimension. Now here, I'm not going to multiply them regularly. So it's not one matrix times another one. I'm going to do a dot multiplication, pixel by pixel, value by value. Okay, so if I call this entity inside the bracket, call it Zi for the ith point, then that matrix 3 by 3 Zi dots multiplied, which in MATLAB you do dot multiply, by E equals 0. So that's another way to write it. Okay, and again, if we use singular value decomposition, we can find the entries of E up to scale, or we don't even necessarily need to use singular value decomposition. We can, or if it's just 8, if you only have 8 corresponding points, then you solve for 8 equations and 8 unknowns. Singular value decomposition is good when you have more than 8 points, so you have more equations than unknowns, and you can use singular value decomposition. But anyways, from these equations, you can find the entries of E, and you can find this matrix up to a scale. Now that I found E, the question is, how do I go back and find this T, and how do I find this R? Once I know those, that means I know the pose of my camera. Okay, so let's go ahead and talk about calculating the pose of the camera. So as we said, E is singular, and we can find the elements in E up to a scale. For that reason, also, we cannot find both T and R perfectly uniquely, and what we can find for T is really the direction of it, not the magnitude of it. The magnitude of t we cannot find, but we can find the direction of t. If we apply singular value decomposition on E, as I mentioned earlier, it has 1, 0 singular value, and the left singular vector associated with that 0 is the direction of t, t hat. Okay, so that's how we can find the direction of t. Then we can also mathematically show that we can find the rotation matrix R by plus and minus u r of 90 degrees plus minus transpose times v transpose, where u and v are coming from the SVD of the E, and the rotation of 90 degrees is this matrix here, which is a z rotation with 90 degrees, right? So these two are also 0 and these two. So this is cosine of 90 degrees, right? And this is negative sine of 90 degrees. This is again sine of 90 degrees. And this is cosine of 90 degrees. So this is a rotation z of 90 degrees. And if it's negative 90 degrees, then these two will be negated. So you get a negative here and a positive there. So you can get two rotation matrices, okay? And basically 4 of them, not 2 of them. You get 4 rotation matrices. Why 4? Because you have a positive negative here and a positive negative there. So you get 4 rotation matrices out of this formula, and we're going to only keep the 2 that will give you a determinant of r equal 1, because 2 of them will give you a determinant of r equal negative 1. Since we are in a right-handed system, we are not going to use this. We're going to use this one, because again, our system is a right-handed system. Okay, so we keep 2 of the r's. And that means we have now 2 pairs of solutions, right? Because we have 2 r's, and we can have up to 2 t's as well. So which one of these pairs do we keep? By the way, these 2 pairs, we call them a twisted pair. And to see between these 2 pairs of t and r, which one we are going to keep, which one do we keep? We keep the one that has what? We keep the one that has the largest number of points in front of both cameras. Because for one pair of R and T, these points P that we'll find later will be in front of the camera, most of the points. For the other one, the points are going to be here behind the cameras, most of the points. So we'll calculate the location of the physical point P in them and see which one are in the positive direction of x1 hat and x0 hat, and which one are in the negative direction mostly. We keep the one that has most of the points on the front of the 2 cameras. We keep that pair of T hat and R. By the way, this property that the points must lie on the front of the cameras or at the positive distance. Which distance? This D0 or D1, these ones. The fact that these guys have to be positive is something in the literature, we call it the chirality. Hopefully I'm pronouncing it correctly. Okay, so this is how we find what? R and T hat, and as I said, we can never find perfect T uniquely with magnitude because of E being a singular matrix. Okay, so this is the part for that. Now, a couple of things that I need to explain for you. One is when you have noise. When you have noise in the image, or when you have errors in detection of these corresponding points, what's going to happen? That's one thing. 2, how do we find the location of this 3D point P? Okay, so the answer to the first question is if you have inaccuracy due to noise or due to problems in finding the corresponding points, then the singular value decompositions that we have done earlier and we found the R and T, those are not going to be accurate. Remember all that we did up here? They're not going to be that accurate, right? And in this case, they found that in order to find a better estimate for E, and as a result R and T, we transform those points x hat I and x hat j such that the centroid of them lies at origin and the variance of them becomes 1. If we can do that, then the estimate for E is going to be much more accurate and better. The second problem is how to find the location of the 3D point P. So the problem of finding the 3D position of a point in the word frame from a couple of corresponding locations, basically those xi and xj, right? And known camera position is called triangulation. So now that we have estimated R and T, right? So we know the position of both cameras, right? One of them we assume at origin with R of identity, the other one at T and R. And we also know the points xi and xj, or x0 and x1 on both of them, right? These guys, where x here is the pixel coordinate, right? From here, we should be able to do a triangulation and find the location of the point. So we say, hey, this is point x0 I found in this image. This is point x1 corresponding to x0 I found in the other image, the pixel coordinates. Also, I know the center points of each camera, C0 and C1. In order to know C0 and C1, remember, you need to know the K matrix. Okay, and we assume that we do. So if I know the K matrix, I can find these centers for these cameras. And since I know the R's and the T's, then all I need to do is to draw these lines V0 hat and V1 hat, which connect your center of the image frame to the desired, to the point of interest x0, and similarly C1 to x1. If we call them V0 and V1 hat, these two should ideally intersect exactly at point P. The problem is, though, because the correspondence between x0 and x1 is not perfect, this x1 that you detect might be a few or even 1 pixel off with respect to its actual position. Okay, so instead of being that perfect, exactly going at this ideal point P0, they would intersect, but at this point here, that is a little bit off from P0. So now what do we do? Remember, you have other points that your camera has taken pictures. So you have this point P1, you have this point P2 here, you have point P3, and so on and so forth. You have a bunch of word frame points that they have their own projections and their corresponding points on these two frames. So now from those points that you have, you find what? You find the one that is the closest to this intersection point of V0 hat and V1 hat that you found. So this point you can easily calculate, and then now look from all of these word points, which one of them is the closest to this. You find that, and that is your actual point. Now here, let me move this guy up a little bit, down a little bit, and do a little bit cleaning. So if I want to formulate it for you, the goal is to find the minimum of this norm, which is Cj plus djv hat j minus p. What is this? This here is the beginning of the line. This is the direction of the line. This is the distance on the line. So this is the coordinate of any point on this line at the distance dj, right? So that is one point on this line, v hat j, and this is the distance of that point to point P. You want to what? Sum this up over all j from 1 to n if you have n points in the word frame, and see that which P is going to minimize this norm. Because remember, Cj is known and Vj is known. The only things we don't know is P and this distance dj. So we can do a least square optimization, and you find both P and dj. dj is the distance to the point, and P is what? The actual physical point. And you can show that the least square solution for P comes from this formula, which is basically a pseudo inverse, right? So here I is the identity matrix. You have Vj hat transpose, and here the same thing but multiplied by Cj's. This first one is summation, it's inverted. The second one, the summation is not inverted. And so ultimately this is going to be like a 3 by 3, and this is going to be a 3 by 3, and so you end up with sorry, this second one is a 3 by 1. You end up with a 3 by 1. Okay, so this is the problem of what? Finding the coordinates of the points, and again from this optimization you can also find the distances, these. So that was noise, and that was what to do with noise, how to find the location of the point. So now this is our entire structure from motion, because not only we learned how to find R and T from the essential matrix E, right? We learned how to do it. We also learned how to find the coordinates of this point P. Now, some technical difficulties before I finish this video. A couple of technical difficulties. One is sometimes you don't have 2 frames, you have several frames, multiple views, multiple pictures. The app that you have on your phone, you go around the object and you take several pictures. How do you do a structure from motion when you have more than 2 frames? The problem is similar, so you need to find these points of interest in all of these frames, or at least in a portion of them. And then basically once you know they are corresponding to each other, now you have to what? You have to find the relative position. So if you say this one is the center of it is at 0, and the R for it is the identity. Now the goal is to find T and R for this one with respect to 1, and then find 3 with respect to 1 also, and so on and so forth. Okay, so you find the T and R for each one of these frames 2, 3, all the way to n with respect to frame 1, and that is what I mentioned here. And then all of the poses can be transformed into a common coordinate. As I say, most of the time, frame 1. Now that all the camera poses are computed relative to camera 1, okay, then we can also what? We can also find the values of the x, y, and z for this point P. And of course, since I have more than a pair here, the problem is with my triangulation, I'm going to have problems, and the problem is going to be bigger this time, because last time I only had 2 rays, and these 2 rays intersected somewhere that was close to the actual point. Now imagine there is a third camera here, so now I have a third camera right here. And this third camera also give me another ray, right? And this ray now comes and goes like this, let's say here. So now these three lines will definitely might not intersect at a single point. Instead of one intersection point for all three lines, now you might have what? You might have, as you can see, this is 1 and 2, this is 1 and 3, and this is 2 and 3. So now you might have 3 separate intersection points. And this makes the job harder. Okay, so in general, the more frames you have, the corresponding points can have more errors. Those intersections will have more errors, and the error can accumulate. And this accumulation of error is called drift. Okay? And I told you why, because the localizations can have problem, the matching points, the image can have noise, the calibration camera of K matrices might not be accurate, and so on and so forth. So you will have a drift. Now, one way to reduce the drift is to what? Is to use a nonlinear optimization algorithm called bundle adjustment that will refine the poses of the cameras that you found and the 3D points all together at the same time, so you get the best intersection and you get the best result. This bundle adjustment needs a lecture of its own. I'm not going to talk about it in this video, okay? But this bundle adjustment is something that allows, when you have several views, to get a little bit more robust result. That is one thing. And the last thing I want to mention is sometimes you don't have the K matrix. So far we assume that we know the K matrix, and K matrix was essential here, remember, when we basically found the coordinates of the points, not in the pixel frame, but in the camera frame, right? Not in pixels, but in the camera frame, x hats. We assume that we know the K's, but sometimes we don't know the K's. And you might say, how come? Well, because these images I did not take from my own camera. I took them from the web. Or I took them from a camera, but I have not calibrated it. And now I don't have that camera anymore. So if for any reason you don't have K, now the life is a little bit harder. You cannot find these X hats anymore. You have to deal with XJs directly with the pixel coordinates. If that's the case, what happens to this equation that x1 hat transpose ex1 x0 hat was 0? Now what happens to it? Now your x hats are kj inverse times xj. So x0 hat is going to be what? It's going to be k0 inverse times x0. And your x1 hat, which is going to be k1 inverse times x1, since you transpose it, the order is going to be inverted, so you get x1 transpose times k negative 1 k inverse transpose, and this negative 1 transpose is shown as negative t here. So your equation becomes this guy equals to 0. And now if you call this interior matrix, matrix F, which we call it the fundamental matrix, it's not called essential matrix anymore, it's fundamental, is related to essential by K1 negative transpose, K0 negative 1 or inverse. So fundamental and essential are related through the calibration matrices of the two cameras. Okay? And now your epipolar constraint becomes this. The problem is this F matrix, just like the E matrix, is a singular matrix. And in this case, if you do singular value decomposition on F, you can write it this way. One of your singular values will be 0 because this is a singular matrix. And that 0 singular value will give you E1 for its left singular vector and E0 for right singular vector. So you can find the epipoles if you want, but the remaining part of it, which is this homography, H, that homography cannot be uniquely determined. So from this homography, you cannot find R and T in a unique way. Okay, so that makes it a lot harder. Now, is there any solution to it? Well, there are some solutions, but again, those solutions are not the topic of this lecture. If I have time in a separate lecture, I'll talk about if you have only the fundamental matrix and you have pictures from the web, can you still do structure from motion? You know you can, probably from some of the pictures you have seen around, but the literature of that and the technique of that is a lecture of its own, which I try to cover later, as well as what the bundle adjustment. So this is the theory of structure from motion, and if you want to see relevant code, here I have two relevant code for you, which I got both of them from MATLAB help, so none of this code is mine, and I'm not gonna publish them for you as my own code. I just give you the link on where you can find this code on MathWork website. So the first one is from a couple of frames, left and right, is kind of like a stereo, that are taken from this globe, this airplane, this whiteboard, this elephant, and so on. And they are directly read here from MATLAB Toolbox. You read them in and you show them. Then you load their intrinsic matrix here, okay? So here you have the intrinsic matrix. You know it. They are both taken with the same camera, and you know that K because it has been calibrated. You get it? And then what? The first thing you do before finding the corresponding points, you remove the lens distortion. You can do that once you have the K matrix. Seems like here, let's see. Let's go back. So here you can see that the intrinsic parameters is given. You see even you have K, and if you want you can show K. So here you can see in intrinsics, right, dot K, and it should give you the K matrix here. Let me run it again. So I can show you the K matrix as well. There we go. So you see the K matrix is there. You remove the lens distortions, which you can do, as I said, once you have K matrix. You find the corresponding between the points, and this is done using the method detect main eigenfeatures. Okay, so it finds a bunch of feature points. Okay, it detects them and then it matches them by doing this vision point tracker. So you find some match points between them, and you can show them here. You see by a green plus and a red circle. Right here, the two frames are put on the overlaid on the top of each other, and you can see them, these corresponding points right here, right at the bottom of the trunk. You can see, or on the top of the, let's say, the nose of the airplane, the propeller, the sphere, the globe, and so on, right? So it can find the corresponding points. Now here, this is where the error can happen. Okay, even if it's 1 pixel, these corresponding points, if you zoom in, might not perfectly be on the top of each other. Then from here, you estimate the essential matrix E, right? So here, if you want, you can say, hey, give me E, and it should give you E, right? So this is done with this built-in function called estimate essential matrix, which is using all those formulas I showed you. It should give you the E matrix, and then it goes back and with this E matrix, double check again on the matching points, see which one of them are outliers with this E. So it reprojects the points from one image to the second image and see if they match the detected points. If they don't, it might call them an outlier. Okay, so now it's gonna keep a portion of these points. Okay, you see this point here on this tape here. Those were not good based on the found E matrix, so they are taken off. Some of the points are kept as inliers, and now you use what? You use the method to estimate the camera pose. So once you have E, now it's time to find the T, and it's time to find R. and then to compute the 3D points here. You see here we are using the triangulate. And this triangulate, once you give it the match points and the camera matrix for 1 and 2, that should find you the 3D points. And here the camera matrix 1 and camera matrix 2 are coming from what? Coming from this function camera projection, which you pass to it basically the E matrix and the data from E matrix and the K, and it should give you R and T. And here you see that the first camera is at origin and the identity rotation. Okay, but it finds you camera matrix 2, right, which you can see. This is camera matrix 1, this is camera matrix 2. Give them to this triangulation, it gives you the points right here. You can see these are the 3D points, and now you can display the point cloud. So these are those 3D points that are found, and these two red and blue are the pose of the first camera and the second camera. And here at the end it even fit a sphere to the points on the globe to kind of give it a better 3D reconstruction. Okay, so this is the first one, and the second one here is from multiple views. So here you have 5 views of the same globe, and again here we assume that we know the camera K matrix. Okay, so here again does everything similar, right? And find the points and get the camera poses. Here these are some match points, and these are all the camera poses, 1 2 3 4 5. And then basically show the dense reconstruction here, which you have a lot more points. And in here you have to use the bundle adjustment as well to get accurate results. And you can see that here. It says use bundle adjustment to refine all camera poses. I have not explained bundle adjustment, but just wanted to tell you. So all you need is to go to basically computer vision image processing toolbox, and I put the URL for them if you want to see them on MathWork website. So thank you so much for your attention, and I'm going to see you in the next video. Thank you.